Greetings to everybody watching me right now. Welcome to Shexa's YouTube channel, where you learn technology and other things related to technology with Shexa. If you are new to this channel, please make sure you subscribe and you leave your like, you comment, you share, and you click on the notification button so that you don't miss out any new video that we're going to upload. Today we're going to talk about how one can access memory when programming x86 microprocessors. Sorry for that, I was just putting my phone on the charge. Right, so today we're going to look at how one can actually access memory. That is, we are trying to access anything that is residing within the random access memory. So for us to do that, we will start by looking at our variables, and since variables are defined as a named storage location or a named memory location, so we want to access where that location is. Thus accessing memory. We want to access data or whatever that is within memory. Right. Secondly, we will look at how one can calculate a physical address given a certain assembly language program, or given a certain 16-bit address with respect to a certain segment register. So from there, we then look at registers used to access memory. But before we do that, I will give you the reasons why we need to calculate the physical address. Then we look at the registers that are used to access memory. Practically, we practically access the memory. That is, we then write the instructions that are needed for somebody to access memory. So that's the outline of today's lecture. So before we get into business, please give me more likes. I want to see more likes. I want to see more likes. Yes, the number of viewers, the number of people that are watching this video must match the number of likes that I have on this YouTube. So that's it. Let's now look at variables, variable declaration, or the directives that are used to declare variables and what they mean. So in assembly programming language, the variables are defined or declared by bytes. This means that whenever we are declaring a variable in ALP or assembly language programming, we use bytes to state the size of our variable. For instance, in C programming we say int, and we know that by saying int we are actually stating the size of that variable and the type as well. But here in ALP we do not state the data type. The variable that we declare can take any value, but make sure that the value that you initially put is the same type that you're going to have in your variable, or you may change it later if necessary. So db, as I said earlier, I said all variables in ALP are defined using bytes. So if you want to define 8 bits, you say define byte. So that's 1 byte. You see where and when to place the db. So the db is the keyword that we use to define a byte. And then if you want to define a variable of size weight, you say define weight. You say define weight. So if you want to declare a double word, that is 4 bytes, you say define D or DD. You say define double word. I will try to go slowly so that you understand what I'm going to explain or describe in this lecture. So that's it on DD. I think this is straightforward. DQ, define quad word, that's 8 bytes. Define 10 bytes, that's 10 bytes. So these DB, DW, DD, DQ, and DT, these are the keywords that we use. These are the directives that we use. So the text that is following here, this text that is following this one, to say define byte, it's telling you that DB is used to define a byte, DW is used to define a word, DD to define double word, DQ to define quad word, DT to define 10 bytes. Right. So I'm sure that in any one of the earlier courses or any prerequisites of this this course or these concepts that we are going to I'm teaching you, you must have done number systems. So here are the number systems that are accepted or that are used in assembly programming. We have decimal, octal, hexadecimal, and binary. So these number systems, they are represented by a certain value, a certain character. O stands for octal. It's either a capital letter O or a small letter O. H for hexadecimal, it's not case sensitive. B stands for binary. D for decimal. So these are not case sensitive. So these are the directives, and these are the number systems that we have and that we are going to use in this lecture and in programming microprocessors. Right, let's now look at the syntax of declaring a variable in assembly language. Like I said earlier, DB stands for define byte. If you want to declare 10 bytes, you say DT. You see, so whenever you are declaring a variables, you don't need to state the data type. So no data type declaration. And here is the syntax. You start by giving a name to your variable. So the name, that's this variable name that we have here. And then we have variable size. That's where you say define byte. So variable size is replaced by DB or DW or DD or any of those directives that we have discussed in the previous slide. And then you put the value. On value, you can value can be any numeric value in any supported numbering systems, that is hexadecimal, binary, or decimal, or a question mark symbol for variables that are not initialized. So if you are not initializing any of your variables, you put a question mark in place of value. Right. So variable name can be any letter or digit combination, though it should start with a letter. It's possible to declare unnamed variables but not specifying the name. This variable will have an address but no name. Right. So that's it on the syntax. But let's now look at a practical example of how one can declare a variable. Let's open this program. Right. So with this program, let's look only where we are declaring a variable. Right. The variable that we have declared here is we have declared var1, variable 1, and it's of size byte, and it's initialized to 7. Variable 1, that's the name of our variable, initialized to 7, and it's of size byte. So I can read this line of code saying define byte variable called var1 and initialize it to 7. So that's our variable declared. The variable is now declared. Let's now look at the other variable declared within this same program, where var2 dw, it's now a word. If you can look at it, it's now a word, and it's given a hexadecimal value. The previous variable var1 was of size byte, and it was given a decimal value since it doesn't have any character appended to it. So var1 is a byte variable with a decimal value 7. Now we have another variable, which is what? Which is a variable var2 of size word, initialized to 1, 2, 3, 4 hexadecimal value. So that's our second variable declared within this program. Then if you want to leave any of these variables without initializing, you can put a question mark in place of 7, or you can put a question mark in place of 1, 2, 3, 4 h, meaning to say the value is not known yet, but will be assigned to our variable. Right, let me give you a takeaway. By takeaway, I mean just a homework or practice question. Write an assembly program to read 2 decimal numbers, then multiply them together, and finally print out the result in decimal. Right, let me reread. Write an assembly program to read 2 decimal numbers. It's reading 2 decimal numbers from the keyboard, from the user through the keyboard, then multiply those 2 numbers and print out the result, and the result is in decimal. So you are adding 2, you are reading 2 decimal values, you multiply them, the result you print it out, which is still in decimal. So that's it. And here is another program example where we have our variables declared. In this program we have so many variables declared, and some of them are initialized to nothing. So we have num1 of size what? Can I see on the chat section or on comment section the value that is initialized to our variable num1? I want to see answers. I will count 1 up to 5, 2, 3, 4, 5. Right, so our num1 variable is of size byte, and it's initialized to nothing, so that's why we are having a question mark there. This question mark means we have not initialized this variable with any value, right? So we have another variable which is num2 without any value initialized to num2. Same applies to result. Result is of size byte, and it's initialized to no value. So the question mark stands for blank value, as we are accepting values from user from the console. So this one is more like a hint to to the takeaway that I've given you some seconds ago. Right, here is another variable declared and initialized with several types of values. Right, we have our variable called message1 of size byte, initialized to 10, 18, and a string which reads enter first number to multiply. So this line is a declaration of character array. So we have a string of values, the first value being 10, the second value being 18, and then the third value being a string, which is an array of characters. Then the second message that we have is message2, variable defined as byte with the 3 values as well. We have 10, 13, and a string, just like message1. So we are telling, or we are prompting the user to enter the first number to multiply, then enter the second number to multiply as well. Then the third message, or the third variable that we have is message3, which is a byte with these values. So we do not need to say we do not need to tell our assembler to say this is a string, this is an array, this is a string, this is an integer, this is whatever. We don't need to tell our compiler about that. You will see it on one of the lectures that we have when we will look at arrays. I think that's the next lecture. We will look at arrays. So this is a typical example of an array. We are having 1, 2, 3 bytes, 10 being the first byte, 13 being the second byte, and then that string being the third byte. Right. So you will also learn how the numbers on message like 10 and 13, 10 and 18, what do they mean? By that I mean I'm referring to these values, 10 and 18, 10 and 13, 10 and 13 as well. You may read this comment. The comment tells you what these numbers works. 10 and 13 works as new line character and so forth and so forth. We will do some experiments later in one of the lectures that we will have and test if we change those values, what happens. Right, so this is a piece of code that I selected to show you the whole code. I cannot give you the whole code because I've given you a question which I think you should do as an assignment. That's a takeaway. So go and do that one. I just gave you a hint on prompting the user to enter the values to be multiplied. Right, so on variables I think we are good. We are now good to go. And if I ask anybody to declare a variable, you can declare it. So on the chat section or on the comment section, please define a variable of size 16-bit. Define a 16-bit variable called my name and initialize it to Shexa. Define a variable of size 16-bit and initialize it to Shexa. I want to see the solution or the answer on the comment section. I will repeat the question. Define a 16-bit variable that is going to be initialized to Shexa. Right, so I will give you mine, which is not going to be printed out here, but the one that I'm going to give you is this. I will just say my name, DW, that's a word is equal to 16 bits, or 16-bit. Then I put a space and then say in double quotes Shexa. I will start again. Then I will do this. I will say my name DW. Then I say in double quotes Shexa. But if you want to print it and you don't want to complicate on going to the next line and other things, that's when you put those values, like you say my name DW 10,13 space, then you put in double quotes, you put Shexa, and then a $sign within the double quotes. Then that's done. We are done on declaring that variable, right? I want to see more likes coming to show that what we are learning here is being understood. So before we go there, we'll come back to this one so that you see what I'm saying. Here we've declared these variables. We have that one, message 1. So message 1 is declared like that. You see that message 1. So message 1 is defined as, message 1 is the variable name db to say defined by. So in this case we will say my name define word dw 10, 13, or 18, then you say double quotes, you say Shexa, $sign, you close the double quotes. That's the solution to the previous question that I gave you. It's not written anywhere in this slideshow. Right, let's now talk about other things that are very important and so direct to how one is accessing memory. So a register is a storage location. Like I said previously, I said a variable is named the storage location, and now I'm saying a register is a storage location as well. Memory address formed with two registers is called an effective address. Since x86 registers are 16-bit, the effective address will be of size 16-bit. Physical address is the address of a memory location that is in RAM. Right, so this is very important. We want to look at how one can access memory location that is in RAM, and the locations are in sizes of bytes. Right, so previously I said I will tell you why we need to calculate the physical address. Right, so before we talk about calculating the physical address, I will tell you this. Here it's saying since x86 registers are 16-bit, you see the effective address will be of size 16-bit. So all the registers that are used in x86, they are of size 16-bit, right? Right. So why then do we need to calculate the physical address? The bus that carries data back and forth, microprocessor, it's of size 20-bit. Physical address is of size 20-bit. You get what I'm saying? So physical address is of size 20-bit. Why? The address bus is of size 20-bit. So Intel 8086 has 20 lines address bus given a 16-bit effective address. That's the address that fits within x86 registers. You must be able to calculate the 20-bit address. You must be able to calculate 20-bit address. So given an 8086 code to access memory, you must be able to calculate effective address, hence the physical address. So let's look at this. let's define what an offset is. An offset is the displacement of the memory location from the starting location of the segment. Let me say you are in a room, right? And then you say, I want to move 3 steps from where I am. You see, I want to move 3 steps from where I am. Right. So, what is the offset? The offset is more like I'm saying, where are you starting from and how many steps are you going to move from the place, from the location where you are right now. So the starting address is the one that we are saying, the starting address, that's the effective address. So the location, I think you will see it when we illustrate on the next slide. So offset is the displacement. It's just the number of steps that you move from the starting address. So it's the number of steps that you move from the starting address. So let's now say, given that the value of data segment register is quad 2 hexadecimal value, right? To convert this 16-bit address into 20 bits, what the BIU, the bus interface unit, it appends a 0 to the least significant bit of the address. That is multiplying data segment register value by 10, which gives us quad 20. Sorry for that. So after appending the 0, the starting address of the data segment becomes quad 20 hexadecimal value. Right. So you get it, you get what we are saying here. So given that data segment's value is that, given that this is the data segment value as said on this slide, right? The BIU then appends a 0 by multiplying DS value by 10. We now get the logical, the starting address as or data segment becomes quad 20. Right. Now if the logical address is given like this, to say quad 2h, then colon 0016h, then this means that 0016h is the offset and quad 2h is the value of the segment register, in this case being data segment. Right. You know other segment registers that we have with extra segments, text segment, and code segment, right? So that's what we have. And then what's next? Physical address is now so on this line we are saying if the data at any location is a logical address specified is quad 2h colon 0016h, then the number 0016h is the offset and quad 2h, that's the data segment value. To calculate the effective address of the memory, BIU uses this formula that I'm going to give you. Effective address is equal to starting address of segment plus offset. Starting address of segment plus offset. So this is how all those things are calculated. Therefore, our starting address is this one, the one calculated earlier, which is quad 20h, and then the physical address we then add our offset. So after adding our offset we get our physical address, that is PA. So the formula to calculate physical address is 10 times data segment, or it's 10 times segment register plus offset. So this one is that one plus that one. So I think it's wrongly written here. Right, so that's how it should be written. Right, so that's it. Here you can see the formula here. We now say 10 by segment register plus offset. And then what's our offset? If you multiply that, you get that, and then our offset is 0016. So it means from this starting address, I'm going to move 16 steps to the location where I want to get the data from. Right. So therefore, our starting address is that, and then our final address, our final physical address is that one. Right. So that's it. Let's go to some illustrations. Right. So let's say here is our demo example, memory addresses. So this is the memory address. You may be given only this, and you'll be asked to calculate the physical address. Given this address, how do you calculate the physical address? The data segment is quad 2, then offset is 0016. So you say that multiply by 10 and so on and so forth. But all those calculations, what they mean is this. This is what all those calculations mean. Why did I prepare such an illustration? The one that I'm going to show you, so that you don't claim, you just understand it, you know it, you will reproduce it anywhere, or you can use it or apply it anywhere where it applies. So here is our memory addresses in sizes of bytes. Then we have byte 0, byte 1, and so forth. So in other words, we are saying this is our data segment. This is our data segment with starting address being byte 0, second address being byte 1, byte 2 following, and other addresses, and then we get to the addressed byte. Right. So how do we get to the addressed byte, which we have calculated before? And the one that we have calculated before is 2236, if not mistaken, 22236H. Right. So we have our data segment right like that with all those bytes. Then the starting address, our data segment registers that. Then how do we calculate the starting address? We multiply data segment register by 10. We get that starting address. So this is our starting address. This is our starting address. Now we want to move from this starting address. How many steps? 16 steps. So we move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So those are the steps up until we get to that addressed byte. You see, that's what is happening. Our starting address, that's the starting byte, which is of size 8 bits. Then we get this physical starting address by multiplying segment register by 10. We get the starting address. Then our offset is 0016. We move 16 steps up until we get to 22236. So that's it. Let's look at how it goes. We have our register like that. We move 16 steps. That is those are the 16 steps up until we get to the addressed by. So I now know or assume that you know how and why we calculate the physical address. We calculate the physical address because all the registers that we use in x86, they are of size 16-bit, and the address bus that we want to use to transmit data from memory and to memory, they are of size 16-bit. It's of, sorry, the address bus is of size 20-bit. So to convert from 16-bit to 20-bit, we say segment register times 10 plus offset. That's it. Right, so to access memory, we can use certain registers. So let me check. Right, so we are done with this one. More likes, please, more likes. If you haven't subscribed, please do so before the end of this lecture. I may fail to give you the link to other lectures, or we may fail to keep other lectures online. So you need to make sure that you attend to these lectures. You may fail to download these lectures because of some restrictions that may be imposed on these YouTube content by YouTube. So make sure you subscribe, you like, you comment, you share, and you click on the notification bell. If you do that, you will never miss any video that Shexa uploads on this channel. Right, so to access memory, we can use the following registers. We have BX. So in general terms, we use base registers and index registers. So base registers and index registers, these are the registers that we use to access memory. And which base registers do we use? We use BX and BP registers. So BX, that's base register and base point. Then we have index registers. Index registers, we have source index and destination index. So these are the registers that we use to access memory. And this is it. BX, SI, and DI registers, they are used with the data segment register. The data segment. And data segment register is the one that is used with these three registers. Don't confuse this, please. Don't confuse this. Data segment, by this I mean when you want to calculate the physical address given BX, you know the segment register to use. You use DS. If you want to calculate physical address given SI, SI value becomes the offset, DS become the segment register value. So you know what to do. Let me repeat myself on this one. I am saying BX, SI, DI, and BP. These are the four registers. These are the four registers: BX, SI, DI, and BP. These are the four registers that we use to access memory. Don't mistake or do the wrong thing or misunderstand me on this one. These are the four registers that we use to access memory, right? But if you want to access the memory, or if you want to calculate the physical address, DS, that is the data segment, is used with these three registers, right? But now, if you want, if you are given base pointer and stack pointer, these two registers, BP and SP, they are used with stack segment. They are used with stack segment. Don't say SP is now used to access memory. but I'm just saying if you want to calculate the physical address given SP register, you use stack segment, right? So that's it on there. So by default, BXSI, I'm just concluding what I've said. By default, BXSI and DI registers work with the DS segment register, and BP and SP work with stack segment register. That is, other general purpose registers cannot form an effective address. Also, although BX can form other general purpose registers cannot form an effective address, then BX can form an effective address, but BH and BL or BH or BL cannot form an effective address. By effective address, we mean that offset, the one that we add to the starting address of our segment register. So by combining these registers inside the square brackets, we can get different memory locations. I will show you the supported combinations, or the supported combinations of these registers. The supported combinations to use if you want to access memory. Right, I hope you understood all this. I hope all this is being understood by you guys. I don't get tired of getting likes. I don't get tired of getting positive comments. I don't get tired of getting likes and comments. If you see me missing something, don't leave me proceeding without correcting me. Right, so here are the supported combinations. Right, you can combine BX and SI. Before you confuse yourself with all this, let me say this as you add some likes. Let me say this: base register does not work with another base register. Right? Base register cannot work with another base register. Index register cannot work with another index register. Index register cannot work with another index register. Right? Note this before we go any further. Whenever you see the square brackets, these ones, whenever you see the square brackets in an ALP program, you must know that we are somehow working with memory. We are somehow accessing memory. So the square brackets means the value that is inside the square brackets is the memory address, or is the effective address, or the offset. I think I'm done with this one. Right, so now here are the combinations. I said BX or BX cannot work with BP. SI cannot work with DI. If you see yourself doing this, doing that, then you must know that you are making a mistake, or you are doing the wrong thing. Right, so here are the combinations. The first combination being BX plus SI. If we add the value in BX and SI, then we get the offset. That is the number of steps that we will move from the starting address of the segment register. Same applies, we combine these two values. It gives us the number of steps that we move from the starting address there as well. Then you can use only SI, you can use only DI. You can use 16-bit variables. You have seen us declaring variables, and 16-bit variable is the one that is defined by DW. And if you have DW variable, then it can be used to access memory. You will see in one of the examples that we're going to have today Then you can also use bx alone. So these are the combinations. We are done with these two cells. You can use bx and si with the 8-bit displacement. Same applies bx di with 8 bits, bp with si, bp with the di, and 8-bit displacement. So d8 means 8-bit displacement, is stated below. Then d16 means 16-bit displacement. So you can also use single registers like si with displacement, 8-bit displacement. These registers can be used alone plus 8-bit displacement, or you can combine base register with index register and then you add a 16-bit displacement, or you can use single registers plus 16-bit displacement. I think I have shown you, if not mistaken, I will show you, or I have shown you already. Right, so what is it that we are saying is displacement? Displacement is just a signed value, so it can be both positive or negative, but in general terms, what is it that we are saying is displacement? We are saying, given an offset, to say these are the steps that you need to move from wherever you are to somewhere else. You need, when you get there, you need to move this number of steps. That's the displacement. Displace yourself from where you are so many steps or so many times. So displacement is the number of steps that you move from any given address. Displacement is the number of steps in direction. So if it's positive, you move in the positive direction. If it's negative, you move in the negative direction. Don't get confused. Right, so displacement, that's it. Displacement can be an immediate value or offset of a variable, or even both. Both what? Both immediate value and offset of a variable. It's up to compiler to calculate a single immediate value. Then displacement can be inside or outside these square brackets. Compiler generates the same machine code for both ways. So you may put displacement within the square brackets, or you can put it outside the square brackets. Generally, the compiler takes care about difference between 8-bit displacement and 16-bit displacement, and it generates the required machine code. Right. For example, let's assume that data segment value, or data DS register has got a value 100, and BX is got a value 30, and SI has got 70. I'll repeat this. Let's assume DS has got 100, that is 100. BX has got 30, that is 30. SI has got 70, that is 70. BX plus SI in square brackets plus 5 is calculated. BX plus SI within the square brackets plus 25 is calculated by processor to 100 times 10 plus 30 plus 70 plus 25 to give us 1725. So by default, data segment is the one that is used with the registers that you may have, except those with BP register. They use SS register, that is text segment register. Right, so that's it. Let's now look at some examples. Let's assume that ds is equals to 100, bx is equals to 30, si is equals to 70. That's the question that I stated earlier. Let's assume ds is 100, bx is 30, si is 70. Then what happens? For example, the following addressing mode, that is in square brackets we have bx plus si plus 25. The processor calculates the physical address like our offset becomes bx plus si plus 25. That's our offset. Now the starting address segment register starting address becomes 100 by 10. Then we add the offset, which is 30 plus 70 plus 25, which gives us 1725. Right. So by default, data segment register is used for all modes except those with base pointer register. For these, stack segment register is used. Right. So I'm done with that. I think I'm going to give you a takeaway. Right. When ds contains value 1234h and si contains the value 7890h, it can be also recorded as that. I think you remember from previous slides. 1234 is our what? DS register value. Then 7890 is our offset. Here we do not have displacement. You are required to calculate the physical address. Right. So that's it. Let's now look at some illustrations on how to remember all the combinations. Some might be saying, "Oh, all these combinations, these ones." Let me show you the combinations. These ones. These are the combinations that we are talking about. You need to know all these combinations, but it's easy to remember because I've told you that bx and bp don't work together, si and di don't work together. But you can combine base register and index register, and then you may add 8-bit displacement, or you may add 16-bit displacement. So you choose whatever you want. You may use only one of these registers from these 4 registers: bx, bp, si, di. You may choose one, or you may choose base register and index register, add them. That's your choice. You may also use the combination and then you add either 8-bit or 16-bit displacement. That's your choice. Now let's look at how to remember all these combinations. Right. To remember all these combinations, we have these 3 columns. So the columns that I'm referring to are this column first, and the second column, and the other column. So this column is representing, this one is representing displacement. This one is representing what? Index registers. This one is representing base register. So you may choose 1 or 0 from each column, but you must choose at least one register from each column. So now done. I don't know how I'm going to clear my throat. Maybe I can add some water to this container. My juice is up. Let me add some water so that I can clear my throat as I speak. Right. So these are the columns. So what combinations can we have? You may have only one register, that is bx. You may choose to use only bx to access memory, or you may choose to use only what? bp to access what? Memory. You may use only si to access memory, Or you may choose to use DI only to access what? The memory. Or you may choose to use a combination of BX and SI. Or you can choose to use BX and DI. Or you may choose to use BP and SI or BP and DI. Right? Or you may choose to say I want only BP and displacement. Or you may say I want BP and displacement, or I want BPS plus SI plus displacement. Or you may choose BP, DI and displacement, like that. You may also choose to say no, I want BX and displacement only, like that. Or you may choose BX and SI and displacement. On displacement, you choose either to use 8-bit or 16-bit. The assembler or the processor will make decisions. Then you may choose BXDI. So this is how one can easily remember all the combinations. You choose at least one register from each of these columns. You may choose to add displacement. You may choose to use 2 registers, one from each column, and displacement. So that's your choice. You can form all valid combinations by taking only one item from each column, or skipping the column by not taking anything from it. As you see, BX and BP never go together. They're in the same column. They never go together. SI and DI also don't go together. Here's an example of a valid addressing mode. We have BX plus 5. So BX plus 5 is like this. BX, we replace DSP and we put 5 there. That's one example. And these must be within the square brackets, or BX must be within the square brackets, and then plus 5 might be outside the square brackets. So the value in signal register. In signal registers, we have CS, DS, SS, ES. These are the signal registers that we have. And the value in general purpose register, that is BX, SI, DI, BP, that's called offset or effective address or starting address. Right. So we can have all these combinations. So let's go slowly. Let's go in slow motion. All right. We have our first column, and this is the base register column, followed by index register column and displacement. You can choose to use BX only, or you can use BP only, but you cannot use BX and BP. Source index only, or you may choose to use DI only. You may choose to say no, I want BX and SI, or you may choose BX and DI. You may choose BP and SI, or BP and DI. BP and SI, or BP and DI. You may also choose to say BP and displacement. Displacement might be 8-bit or 16-bit, or you may choose displacement plus SI or BP, BP plus DI and displacement. You may also choose BX and displacement, or BX, SI and displacement, BX, DI and displacement. These are the choices that you may have, and these are all the combinations that one may choose. Right. Let's now get into conclusion, but we don't conclude without code. So here are the practical examples. Right. So accessing memory example 1. Here we are going to open our emulator. So if you have your own emulator, make sure you follow what I'm going to do, but you must listen first. You must listen first. So this is the code. I heard some guys complaining about my code. See, my code says font size. So let me try to increase the font size to a certain value. It's now delay. So let me put 30 here so that we have, right, so that's, we now have my code that size. I hope you'll be seeing what we have here. Or it's now not clear. So I say our program is here like that. We say move this immediate value into this. Like I said earlier, whenever you see the square brackets, we are now talking about memory address or offset. So whatever that is within those square brackets is what we are calling memory address or the offset. So let me put 20 here on the font size so that, yeah, maybe this one is clear. So let's do the code here. Right, so 1234 is our memory address. So we are putting quad 1 hexadecimal value onto this address, right? And then what are we doing next on this instruction number 5? We are now taking the value that we have inserted on this address 1234 hexadecimal address to what? To AX. And what do you expect to see in AX register? Let me see it on comment section. Let me see it on chat section. I want to see the value that is going to be inserted into AX. Tell me. Here we are saying we have moved quad 1 hexadecimal value into memory address 1234, right? So we are now taking the value that we have inserted into 1234 hexadecimal value to AX. Tell me, I want to see answers coming. If you don't know, just give me a like and then let others give me their answers. Right. Thank you very much for your responses. The value that is being inserted into AX is quad 1, the one that we have put onto this address. So let's emulate and see how it's working. So let's emulate. Right. So let's say single step. After running this instruction, we now know that quad 1 has been inserted to, has been moved to this address. Now let's check our AX here. AX has got nothing, right? We are now moving the value that is on this address to AX. Let's check AX as we execute this instruction. We now have quad 1 in AX. So what have we done? We have accessed memory. How? Firstly, we have sent a certain value, a 16-bit value to the memory. And then after that, we have retrieved that same value from our memory to the register. I think you now understand what we are doing here. So let me give you a recap of how this emulator works. I hope I want to make sure that when we do the practicals, you all understand what we are doing. So let me reload here. The instruction that is highlighted in yellow is the one that is to be executed, that is next to be executed. and the address of that instruction is the one that is in IP. So in IP is the instruction pointer which points to the next instruction to be executed. And I think you remember very well when we talked about ORG, when we said ORG, it tells us to say, what's happening here? It's opening in this Explorer, this Opera browser, right? Sorry for that. I was saying ORG 100, it tells us, it's telling us that the first instruction of this program will be inserted on address 0100, which we can see here. The address of this instruction is here, 0100. If you want, maybe I can change here from 100, maybe I can put 2 there and check now. Let's check, let's emulate. What I mean, right? By default it doesn't go that way anyway. Let's just leave it on 100, right? So this instruction is there, right? We have instruction pointer is 0100, then we move our values, we move value to that memory address, we take value from memory address to AX. That's it. I think this is just a single example, and here we are saying what? This is direct addressing mode. Watch out for the next lecture about addressing modes. I think it's the next, we will have part 2 of this accessing memory lecture, and then after part 2 we'll have another lecture where we'll be looking at addressing modes. So if you want to read in advance, you must know that this is what? This is direct addressing mode, right? So that's it. Let's close it and save no changes, right? So that's accessing memory example 1. Let's look at example number 2. All right. Here we go. Somebody is confused. Don't get confused because we are having a lot of text on this code. This is just telling you where the first instruction is going to be stored in memory, and this data is telling us that this is the instructions that are following this statement. They are within a data segment. Then we go to code. Then these are the code instructions we have in code segment. So beta is a what? Is a word variable initialized to 1, 2, 3, 4. So beta is a variable. Hence it like I defined earlier. A variable is a named storage location. It's a named storage location, right? So beta is a variable, hence it already have an address, and in that address there is a value 1, 2, 3, 4. So we are just labeling to say we already have our memory, and our memory is given in numbers that we do not understand, right? So we want to name a certain location, a certain memory location. We name it beta. So by saying beta, that beta has got a memory location value, which is in form of a hexadecimal number, right? So beta is representing a certain memory address, right? So when we say move a x comma beta, we are moving what? What is it that we are moving to? To AX. we are moving the contents of beta, or the contents of memory location where beta is. So the memory address and the variable name, they are used interchangeably. So if you know the address of, let me say it this way, let's say you want to go to Shexa's house, you may remember the name Shexa and you know where to find Shexa's house, right? Some might remember the address to say it's 9269 Ruyumbo or 9629 Ganyu. So that value is also represented by Shexa's house. You get that? So when I say Shexa's house, I'm saying B9629 Ganyu or Ruyumbo. That's the address. So in place of that address, I may put Shexa's house, or instead of saying Shexa's house, I may put the address. So the variable is the memory address or memory location, but we are just giving it the words that we humans we understand, right? So at this location called beta, we have the value 1234. So 1234 is going to be moved to AX, right? So if we say move to CX, the value that is at address called beta, what are we moving to CX? I want to see answers in the comment section. I want to see answers in the chat section. What are we moving when we say move CX? What is inside the beta memory address, or what is it? We are moving the value that is at beta memory address, or that is at memory location called beta. What is it that we are moving to CX? We already know the value that is within beta variable. So what is it that we are moving to CX? So we are moving the contents of the variable beta, which is what? 1, 2, 3, 4. So 1, 2, 3, 4 is expected to be in CX, right? So if this instruction must not confuse you. We are just saying load the effective address of variable beta into BX. So we are trying to access, to know, to say I have declared this variable, but where exactly is it within the memory? Where exactly is this variable within the memory? So in BX you will see the memory address which can be used interchangeably with beta memory location name, right? So in BX you will see the address of this variable, and then if we want, we can then move the value at one other memory address to DL, and then we are done. So let's emulate this code and check what I was saying, whether it's correct or I was just cheating. Right, so this is what we have. We execute. So this is the next instruction to be executed, right? We want to check our AX. What is it that is going to be moved to AX? What is it that is going to be moved to AX? It's 1, 2, 3, 4, which are the contents of beta. So let's move. So 1, 2, 3, 4 is moved to AX. What if we say move CX, comma, the contents of memory address called beta? Let's check our CX and run one step. 1, 2, 3, 4. So this instruction and that one, they look the same, or they work the same. What I mean is, Here I'm saying give me the contents of a memory location named beta. Same applies here. Get the memory address of beta and get the value that is residing at this address into CX. Right. Now I want to get the address of bx into the address of beta variable into bx. So what is the value that I have in bx? Is 0, 0. Right. So the address of this variable is what? 0, 1, 0, 2 in hexadecimal, right? So let's try to edit. Let's try to get the value that is residing here into dx. The value that is residing within the memory address 0, 1, 0, 2 into dx, right? So let's edit our code. Right. So let's say move dx, comma, the address was 0, 1, 0, 2, and then close that. We emulate. So this instruction is the same as that instruction, so we must have 1, 2, 3, 4 going into dx. I hope you are understanding what I'm saying here. Otherwise I'm going to repeat it. Right. So let's check. AX we have 1, 2, 3, 4. CX 1, 2, 3, 4. Let's now check the address of bx of beta variable. It's 0, 1, 0, 2. Let's now put the value at this 0, 1, 0, 2 address into dx. It didn't come. What happened? It didn't come. Maybe we used the wrong register. Let's just put bx here. Let's put bx there and check. Right. So on 0, 1, 0, 2. On 0, 1, 0, 2, we don't have any value there. We don't have any value there. Let's just I think there's a mistake that we are making here. Let's put an H here because it's hexadecimal, and try again. Run. Let's check bx. Bx we get what? The address of what? Of our variable beta. And then let's check. Now it works. 1, 2, 3, 4. So the mistake was that you need to specify that this is hexadecimal. So what we have done here is that somebody's calling me here. Right. So that's it. I think you understood what we did here. I will go fast and repeat what was happening here. So what we're saying is check. Wow. Here we have declared a variable called beta of size weight, and we have initialized it to 1, 2, 3, 4, meaning to say beta is a variable with value 1, 2, 3, 4, right? And what is a variable? A variable is a named, or is the name of a storage location, right? So there is a location name, which is the variable name, and a memory location value, which corresponds to the name of that location. So beta is representing a certain number system, or a set, sorry, it's not representing a number system, it's representing a certain location, and that location is well known by the computer using a certain number system. It's a value, right? So that's what is happening here. So we've declared our variable. If you want to see our variables, you can click here, and you can see our variables here. We have beta, and the value for beta is 1234, right? You click here on variables, and you can see our variables here, right? And it's of size what, it's of size what, it's of size weight. If you want, you can see it there, then close, right? So this is it. Then after that, you run next instruction, then beta. We now move the contents of this variable, or in other words, we are moving the contents of a memory address called beta into AX, right? We are moving the contents of beta variable into AX. So let's run it. You see 1234 is going to AX, right? Go next. We here on this instruction, we are saying we are moving the contents of memory address given the name beta to CX. Now the contents of that is 1234. It goes into CX, and then we check to say this location called beta, what is the memory address? We want to load the effective address into BX. So we check the address is 0102. Let's move values that are at 0102 onto BX. Then we go that, we check BX 1234. So that's it. If you want to check another the values that are at 2400, you can check and see DL nothing, meaning to say on this location there's nothing. But if we change to say here, let's put DX instead of that, right? Let's say I put 100 there, because I'm sure that at address 100 there is something, so I want to put that something into DL. So let's run it, emulate, step, right? Let's check DL is 34, but now it's EB. So EB is representing the first instruction in this code, right? So these are the comments. They are just telling you how one can calculate physical address given that the DS value is that, physical address is calculated is that, if CX is this one. So given this instruction and given this, you can calculate your physical address as that. All right, so thank you very much for paying attention to this example. We don't want to save anything, but let's just save. Right, let's see another example. I hope we're going to complete all the examples. Right, here is another example. Right, so on this example we are just moving, I think by now you will now understand what we are saying. We are moving the contents of this address into AX. After that, we take the value that is within AL register to this address. That's what we are doing. And here we are saying we take the value that is within AL into extra segment offset address 1234. So the offset address is 1234, but it's within extra segment. That's it. If you want to calculate physical address segment register, use extra segment register's value, then you multiply it by 10, and then the offset is this one. You edit, you calculate you get your physical address. Right, let's look at another example. Register what nonsense. Right, so this is our other example. So here we are saying we move 1 2 3 4 into SI register. Perfect, we all understand this. So we now move a certain value to an address which is within SI. And in SI we have 1 2 3 4. So 1 2 3 4 is the address where we are putting 1 2 1 3, right? So we now want to check the value that we have inserted there, and we want to take it or move it to AX. So what we do is we take that as our source and then our destination, and then we move it. We check, we must see this value in AX. Next we say move the contents of 1 2 3 4 to BX, which is that just the same instruction. This instruction is same as this one, so the value that is in AX must be the value that is in BX. Same applies with other instructions that follows. So here is our emulation. So right, so here what have we done in SI? Where is SI? 1 2 3 4, right? Perfect. So we now want to move 1 2 1 3 to address which is in SI. So we are moving this immediate value into the address which resides in SI register. So let's move it. It's now moved. Let's now take the value that is residing at address. We are now taking the value that is residing in the address that is in SI. So in SI we have the address, but the value that we want is at a certain address which is in SI. So SI is 1 2 3 4, but we are not taking 1 2 3 4 to AX. We are taking the value that is at address 1 2 3 4 into AX. So if we go one step, if you go to one step, the value that is at that address is 1 2 1 3. So that's the one that we are expecting on AX. So we run 1 2 1 3. Perfect. So in BX it's the same. We are taking the value that is at address 1 2 3 4 to BX. And what is that value? We have inserted it here. So why am I saying here? Because SI is 1 2 3 4. So it's more like we may replace SI with 1 2 3 4 to say we have moved 1 2 1 3 into memory address 1 2 3 4. And then here we are now retrieving the value at this address into BX. So let's move single step and check BX value 1 2 1 3. Let me clear my throat. You must buy me more rings to clear my throat. I'm joking. I'm joking. Right, so that's it on these instructions. And then here is another instruction. We are moving the contents that are within the address that is in BX. We are moving the contents, not the contents of BX, but the contents that are in address which is in BX register to CX. So in BX we have a certain value, so we put it there. So if you want, we may put DL to that address as well. So that's the fourth example. The fifth example, I think this is the final example, which is so simple, short. Right, so this one is just an array. Right, it's okay. We've declared our variable of size byte, and it's called num. and it has got these values 1, 2, 3, 4, and 5. So whenever we have square brackets, it means we are dealing with memory at memory address 0, but in this case it's an array, so it's index 0. So we are moving the contents of memory address called num0, since a variable is the name of a certain memory location. And then we put it to AL, and the value is 1. And then we put bx, we put 4 into bx, then we take 4 as the index or the memory of our variable, which is named num, and we are now taking the value that is residing at a location called num index 4 to AL, and this value is 0, 1, 2, 3, 5. 5 is going to be moved to AL, right? So it emulates like this: single step AL. AL is that we have 1, which is okay. Then next you must have 4 in bx. Then we have 5 in AL, like that. Let me check if we have another example, which I think is the last one. Right, this is the last one. This is the final one, the last one before we conclude the day. Right, I think this one is we have talked about something like this but there's something that I want you to there's something that I want you to see here. This is the most interesting example, the most interesting example ever. I want your responses in the comment section, in the chat section. Give me your response in the chat section. Right, so just wait for the question and then you give me your responses. For now, you may click on like, you may subscribe if you haven't subscribed, you may share the link with your colleagues. Right, so here we are defining our constant called beta. Equal is a directive which is used to define a variable, a constant variable, and here we've declared beta. So we in this case we do not specify the size. Then equi is our directive, like I said. Now we move this value into AX. We initialize our DS register. Then from there we take the value that is residing at memory location named beta to DX. Then the value that is at beta is what? 1, 2, 3, 4, like said here. Then we move 1000 into BX. We move BEED, hexadecimal value, into AX. Then here we say move the value that is in AX, which is what? I don't know. That's where I want your responses. What is it that is going to be moved to AX? Is BEED. I'm sorry, I've given you the answer. You give me the second answer, right? So what is it that is being moved? Okay, so it's fine. So I said BEED is the value that is going to be inserted into AX. Now my question is, this value in AX is being moved to where? This is the destination. It's being moved to where? Now you need to know that this is the offset or the effective address. And what is the, how do we now calculate the effective address given this instruction? We say the value in BX, that's the address, right? And then we add it with the value or the address of beta variable, right? So how do we do that? Let's let's check what is the value. Let's open our calculator. Here's our calculator here, right? Let's say bx. What is the value of bx? Bx is 1000, so we say 1000, and this is hexadecimal. Let's tick here on hexadecimal, right? 1000h plus beta. Beta is having what? 1 2 3 4, so we say 1 2 3 4h. So this is the answer. So we are moving the value of ax into this address called 2234, right? So if we want to check, we may clear the value of ax and try to move the value that is within this memory address 2234, which is this one, and check if the value that we get there is BEED. Let's emulate, and as we emulate step by step, I will be telling you, I will be repeating what I've said earlier a few seconds ago, right? So here we are saying move 0200 into AX, right? 0200 into AX, perfect. Now initialize DS register, we don't see that. Then move the value of beta into DX, which is 1234, right? So let's check DX. DX is here, and then single step 1 2 3 4, perfect. BX is got nothing. Let's move 1000 there. 1000 is there. Let's now move AX. Let's now move BEED, hexadecimal value, into AX. AX, we clear everything. BEED is there, perfect. Now we are now moving AX into that address that we have calculated, this one, the one that we have calculated here. That's where BEED is going. So we say single step. So this value has been moved to memory address 2234, right? So if you want to check, we clear the value of AX and then take the value that is residing at this memory address into AX. It must be BEED to prove that the value that we have sent to that address is exactly that one. So let's do it single step, right? Now we have moved the value that was in AX2. We've cleared AX like that. Let's now check, move the value that is within 2234H into AX. It's BEED. That's it. I think we are done for today. Thank you very much for having time with me. Please make sure that you subscribe. Thanks to you. Don't forget to subscribe. Don't forget to subscribe. You like, you give a comment, you share, you subscribe if you haven't subscribed already, and finally you click on the notification bell so that you don't miss out any new video that we are going to upload. May God bless you with distinctions. May God bless you with the best in life. I love you all. Goodbye.